Hello friends, this video on basic concepts of chemistry part 5 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 4. There is something called quantity property. Properties such as length, area, volume, which you can represent in a number. And most of these are observation based, or they can measure. They are called quantity property, where a number is there because you can represent them by a number, and they are called quantitative property. Please note that, for example, you have a wire, you want to find the length of the wire, you can measure 3 meter, 4 meter, right? So those kind of stuffs where you can measure it. Or you have, let's suppose, one big iron ball, you want to find the weight of this, you can use the measuring tool to find the weight, right? So thus you can name it, it is 3 kg or 4 kg. Thus those things are measurable, right? So if you have some water, you want to find the volume of water, you can tell it 3 liter, 4 liter. Thus those things which has numbers related 3, 4, 5, 6, thus those things which you can measure and we can have a number with that, those things are called quantitative properties. Those properties are called quantitative property. The examples I told, right? Length of the room is 6 meter, 7 meter. Here if you see, 6 is a number and meter is a unit. So which will have a number and a unit. Those kind of things are called quantitative property. And there are two different type of system for this quantitative property measurement. One was the English system and the other is the French metric system, which is originated in France. And this is something which is widely used, right? Because it is more convenient and it is based on the decimal system. So we'll learn a little bit more about metric system for quantitative property. There is something called International System of Units, right? SI, which defines all this thing. So this guy, International System of Units, was established in the 11th General Conference of Weights and Measures. And what it says is, it gives 7 base units. It says that there are 7 base units as shown in the tables. There are only 7 base units. And they are called 7 fundamental scientific units. If you don't remember the names, just remember 7 days a week. So 7 base units we have, right? But there are other physical quantities, for example, speed, volume, density. They can be derived from these quantities. For example, speed is distance by time, right? So for distance, we have length. For time, we have time. So using these properties, we can derive other quantities, but they are 7 physical based quantities. And these are length, mass, time, electric current, thermodynamics, temperature, amount of mass, that is mole, and luminous intensity for brightness. So if you see, length is L, that is in meter. We use meter, that is a base unit. Mass is denoted by M, and we use kilogram for this, and we use kg for this. Time is T, we use second for this. Electric current is I, we used ampere for this. We must have learned in physics. Then you have temperature, we use Kelvin, though there is something called Celsius and Fahrenheit, but Kelvin is the SI unit for this. Then you have amount of substance, that is used in SI unit name is mole, and we use MOL as a symbol. And then you have this luminous intensity for brightness, we use candela, and we use CD for this. Let's talk about the definitions of various SI units. I told we have something called meter, kilogram, seconds. But what are the definitions? What is the standard which has this international organization has taken to measure 1 meter? What is 1 meter? So 1 meter, which we see in any clothes shop also, they have this meter to get this meter, or in the meter scale we have meter. But this 1 meter is defined as nothing but the length of the path traveled by light in a vacuum during this second. So you see, it's a fraction of seconds, but we have now, the physicist and the chemistry world has ways to measure these many seconds also, and it has ways to find this distance traveled by the light with a huge precision. And that's why this meter is defined as the length of the path traveled by light in the vacuum during this much interval. And the length that is traveled is 1 meter, and that is true for the whole world. And this is defined by the international community. It keeps changing actually. they find this is not something which is reliable, they may change it. But this is a little reliable because the speed of light is reliable, right? So they look for something which is reliable, because if they somehow find this bar and they say the some bar in Germany, then this bar length may change, right? The temperature goes up, it may increase. If the temperature goes down, it may decrease, right? It is susceptible to the external environment, and that's why they try to choose a base which is really independent. So speed of light in a vacuum is independent. You take the speed of light in any part of the world, it's all same. It doesn't depend whether you are in 0 degrees Celsius or 90 degrees Celsius, or you are in Australia, Canada, India, Japan, doesn't matter, right? The speed of light is same, and that's why they have taken this base, correct? But if you take something, let's suppose a copper of 1 kg, with some dimension they form some bar, right? This length may change. If you are, let's suppose, in US in a colder region, the length will be less. If you are in South Africa, the length will be more because it will expand, right? So those things are susceptible to different environment, but they try to take those quantities which are independent. For kilogram, this is a unit of mass, and for this, it is equal to mass of international prototype of the kilogram. So they have taken one prototype, and that is what that defines the mass of the kilogram. For second, what they have done, it is the duration of these many periods of radiations corresponding to the transition between two hyperfine level of the ground state of cesium-133. So if you take the cesium atom and you try to find the waves of this, and then if you take these many periods, right? So the duration it takes to get these many periods, that is a second. That's again standard defined by the information. The ampere, which is for current, right? It is for the current. So for this, what they are saying is, if maintaining two parallel conductors of infinite length of negligible circular cross section and placed 1 meter apart in the vacuum, please note, these would produce conductor of force equal to 2 into 10 to the power minus 7 Newton per meter of length. So it says that if you have two conductors and you place 1 meter apart of infinite length and negligible circular cross section is very, very thin. If you take two wires infinitely long and you placed 1 meter apart, and then you produce a force of 2 into 10 to the power minus 7 Newton per meter of length. You put this force on these conductors, right? The amount of current that is produced in this, that is 1 ampere, and that's the standard definition of amperes. For Kelvin, this is the fraction of 1 by 273.6 of the temperature of triple point of water. Again, a standard. Mole is for the amount of substance of a substance, right? So this is nothing but I think 12 gram of carbon, but since gram is not the standard unit, we are using 0.12 kg of carbon. We'll explain this when we go to the mole, and we'll have a story of how this mole came, but this is nothing but the amount of substance of a substance which is contained in 0.02 kg of C12 carbon, right? Candela, it is for the luminous intensity in a given direction of a source that emits monochromatic radiations of frequency, this guy 540 into 10 to the power 12 hertz, actually 10 to the power 12 hertz, and that has a radiant intensity in the direction 1 by 683 watt per stereo. These are the standard definitions, because when you say 1 kg, what does 1 kg means? When you say 1 meter, what does 1 meter means? So what are the base of these? So these are the base actually. For 1 meter, it's nothing but the distance traveled by the light in these many seconds in a vacuum. So similarly for 1 mole, it's nothing but you take 0.012 kg of carbon, and the amount of substance in that is nothing but a mole. So similarly, they have defined all these 7 base units, and this keeps changing actually, right? And the prefix they use is, this is my 10, that's called deca, and then you can go to the 10 to the power minus 1, that's called deci, that's called decimal, then 10 to the power minus 2 centimeter, you must have heard, 10 to the power minus 3 is milli. You must have heard millimeter. 10 to the power minus 6 is micrometer. 10 to the power minus 9 is nanometer. You must have heard various manufacturing chips company using nanotechnology nowadays. That is called 10 to the power minus 9. And then we have pico, 10 to the minus 12, femto. Similarly, you have all these values. If you go to this power, 10 to the power plus 2, that becomes hecto. Then you have kilo, 10 to the power 3. Then you have mega. Then you have giga. You must have heard gigabytes, right, of hard disk storage. Then you have terabytes also. You must have heard of storage. Then you have peta, exa. All these are the prefix used to indicate multiples of a unit. For example, I have 4500. I can write this guy as nothing but 4.5 into 10 to the power. Correct. So if you see, this becomes kilo. So this is 4.5 kg actually. If this is kg, it's 4.5 kg. So that's why it is like this. Then you can have, for example, you have 0.12. This you can write as 1.2 into 10 to the power minus 1. So this becomes minus 1. Now we have a question time. We have to convert this into basic unit. 28.7 picometer. So let's start with this. So 1 picometer is 10 to the power minus 12 meter. So 28.7 picometer will be nothing but 28.7 into 10 to the power minus 12 meter, and that will nothing be 2.87 into 10 to the power 11 meter, and that is my SI unit, because this is in meter. This is done. We talk about this 25365 mg. So this is nothing but you have to make in kg, right? So 25365 mg is nothing but 25365 into 10 to the power minus 6 kg. Why? Because 1 mg is 10 to the power minus 6 kg. Because from mg you get gram, from gram you get kilogram. Correct? This is nothing but 2.5365 into 10 to the power minus 2 kg. So if you see, this is my standard unit, kg, and that is my answer. Correct? So the question is that if the speed of the light is 3 into 10 to the power 8 meter per second, find the distance traveled by light in 2 nanoseconds. So distance is nothing but speed into time. So here my speed is in meter per second, that is 3 into 10 to the power 8 meter per second. So my time will also has to be in seconds. Correct? So my time is 2 nanoseconds. 2 nanoseconds is nothing but 2 into 10 to the power minus 9 seconds. Correct? So 2 nanoseconds is nothing but 2 into 10 to the power minus 9 seconds. So we'll write this guy as 2 into 10 to the power 9 seconds. So this you will get in meter. Why? Because second will cancel and you'll get answer in meter. That is 6 into 10 to the power minus 1 meter, and that is nothing but 0.6 meter, and that is my answer. So in this, please note that you have to convert everything into SI unit before applying multiplication. So in this guy was in nanoseconds, I made it into seconds, right? Because second is my SI unit, and this guy was in meter per second. That is correct only. It is an SI unit, and this guy is not in SI unit. So I have to first convert this guy into SI units and then only apply multiplication. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.